college trig results, because obviously you probably know what you got on the college trig just based on like right versus wrong, because Canvas grades it right away, but all the partial credit stuff I still need to go back into. So hopefully that'll bump things up a little bit for some of us that got those questions wrong. We averaged about a 9 out of 13 on the college trig, which isn't bad. Like we did like a day of polar and then a day of review, and like I made you had to like remember all this trig stuff. So I'm not going to stress about it. I don't think you should either. I'm not going to let it make or break you. We're going to get you your college credits, and we're just going to keep rolling on. So, so some stuff coming back to you tomorrow for sure. Obviously, I don't have anything physical to hand back to you for the So You Succeed stuff, but I'll have the physical 3.2 quiz grades if you took it in person, along with your stickers if you get one. But here we go. I have the first half of chapter 4. I don't know if we'll get all the way through chapter 4 by the end of May, whatever the 18th is. And of course, seniors, this is the last thing they're going to get from me.
So I took a look on the first page. I graduated on Thursday.
Do you know what kind of graduation?
What is this? That's a circle. I think it might be a try. Hear me out. Let's try.
Put your name at the top of that front page so it doesn't go missing on you. Folks at home, the link to chapter 4 is right on today's announcement. See that?
Everyone failed. I got it. I like a whole semester. I just did so much extra credit for that.
Okay.
But she doesn't grade the container project. She did.
So you'll see the front page is how they lay out all of chapter 4. Like I said, I don't know that we're going to get all the way through this. I will probably focus in this week on what you have in front of you, and we'll see how much more we need after that. The second half of chapter 4 is very important. I think it gets into like the second derivative and concavity and inflection points and stuff that I've alluded to a lot over the semester, but we just haven't gotten there yet. But I think it's going to be very helpful to anybody, whether you're taking AB, BC, or maybe you're graduating and you have to take a Calc 1 or something to fulfill your math requirements, whatever. I want to make sure that you've at least seen it, heard it, before you see it again. For the folks in BC, it's going to be very, very critical that you have a chapter 4 background for sure. Okay. What I think, and I'm talking to Lynch, the most important part is the first half, which is why I'm doing the first half first. And then second half, we'll do the best we can. But you'll see that here in Unit 4, we've got applications of the derivative. This is only part 1. If we did have time to do chapter 5, that would be part 2. Lynch will pick up. Anybody going to BC? Lynch will pick up where I leave off. Okay, so you will not miss out on anything. It might happen over the summer, though, so kind of keep an eye on that. I'm guessing Canvas isn't going away, even if we're back full time and everybody's vaccinated and all that good stuff happens. I think he'll just kind of pick up wherever we leave off, and my guess is that starts in chapter 5. Because I think with the 12 days that we have minus this Friday, well, it'll work for you. I just won't be here to help you, but baseball is in Grand Junction for the weekend, so I will not be here this Friday. And there also is a chance that I'm not here this Wednesday. There's some stuff at my house that I need to be home during the day for. Like my ADT has to come and like fix my alarm system, and our dryer just died last night. So I have to like be an adult, which sucks. I'd much rather hang out with you guys during the day, but I think I might have to be home on Wednesday because ADT is coming like between 12 and 5. Cool, thanks, yeah. So we'll see, but we'll do the best we can. I will let you know if I'm not going to be here, and of course it'll be a practice day because we're going to learn whatever we need to between today and tomorrow to at least kind of work through the first couple lessons. And what we're going to look at here in the first couple lessons, go ahead and flip the page, is something called implicit differentiation. Okay, because we've done it all. We have done every function possible at this point. All polynomials, all rationals, all the algebraic stuff, all the transcendentals, trig, exponentials, logs. Like I think we've done it. We've looked at every possible function. What it's time to start looking at is how do I deal with things that maybe aren't explicitly written as a function of x. And when I say explicit, I mean like y equals some stuff that only has x in it, right? And we can do that. We really, what we've been doing so far all semester long has been explicit differentiation, because y is explicitly a function of x. Where you give me an x, there's only one y, and really that means that if I go to an x spot, I go up to a y, there's only one of them, and so the derivative is a function also, which is really nice. But what we're going to have to run into, and don't turn the page just yet, is like, how do we deal with a shape that looks like that? Right? How do I deal with a graph that just isn't a function? Because you plug in an x, there's potentially, in this picture, 2 different y values to go to. And so I can't find a derivative that's a function necessarily, especially if my graph, my relation is not a function either. And what happens with that is that the equations that we have to deal with, okay, is not a situation, right, where y is isolated on one side. Okay, when we talk about equations that are implicit, okay, we've been dealing with explicitly defined functions. Y equals some function of x. Now what we've got is a possibility, all right? Whoa. Right, what we've got now, potentially, is equations where I cannot get y by itself. And it be some function of x, right? There's going to eventually be a y either on both sides or a couple of different kinds of y, right? You got a y squared and a y. Can't solve for it. Not direct. Not without maybe having like a plus or minus in there, and of course that's not a function, and all those kind of things. So instead of trying to go all crazy, say, all right, I'm going to do all this pre-work and get y by itself so that I can try to find dy dx, and that's the notation that we're going to use exclusively probably the rest of the way. Okay, is we're going to use Leibniz's notation because it lends itself better for us, because maybe we have multiple variables within the problem. You know, right? We have x's and y's, and I can't get y by itself. Or maybe we've got r for radius and t for time and h for height and a for area and v for volume or whatever. All right, now we can actually, this is chapter 4, applications of the derivative. Now we can use these skills because we've done it. We've got it all. Product rule, quotient rule, chain rule, sure, like all that stuff. So there. Now let's see if we can do something with it to deal with the situation like we have right here with this last equation here at the bottom of page 248. That one right there. Okay, and since this page gives us a whole bunch of space, I'm actually going to break it up into 2 sides and explain, kind of write down how to do implicit differentiation. Okay, how are we going to find the derivative? So we'll actually do the work over here, x squared, and go ahead and write it again so that it's sitting right here waiting for us. How do we deal with an equation like x squared plus y squared equals 25, where I cannot solve for y explicitly in terms of x as a function? Does anybody know what shape that is, x squared plus y squared equals 25? It's a circle, right? If x squared and y squared are both there, okay, we have some kind of rounded shape. Now, if we were to mess with the coefficients of one or the other or both so that they would be different numbers, like 2x squared plus 3y squared, or even just x squared plus 3y squared, it'll stretch it out. And that'll turn it from a circle out into an ellipse. If we made it x squared minus y squared, it would be that hyperbola shape, like a shape of a Pringle. Okay, it's kind of hyperbolic. It really is. It's a three-dimensional hyperbola. Luckily, we'll just be in 2 dimensions. But if you have both x squared and y squared, it's not a function. Okay, because we need a plus or minus to represent that. So what do we do? Like, how do I get to dy dx? Can we do that? Right? Is there a way to get to a point where we have dy dx equals, right, the derivative of y with respect to x? And what's really nice about this process is we've actually been doing it the whole time, but it was all sneaky because We only had y's and x's separate. Now they're kind of stuck together. There's nothing we can do about it. So let's do this. The thing about calculus that's really nice is that all of the algebraic things that we've been doing to equations our whole lives, adding 2, dividing by 7, square rooting, cubing, whatever, as long as you do the same thing to the left as you do to the right, life is good. Okay, and that's what we're going to do. What we're going to do first is we are going to take the derivative of both sides. We're going to take d dx of both sides. Okay, because if I want to end up with dy dx, the derivative of y with respect to x, I better make sure that x is the variable that I'm keeping in mind here, right? Because I could do d dy of both sides, and that would give me a very different kind of derivative, right? It would give me the derivative of x with respect to y. How quick is x changing as y moves, right? Kind of flipping the whole thing sideways. We want dy dx. We want the slope of the tangent line. We want the rate of change depending on where we're at. So this step early on, I think is helpful to write down, right? These first couple days here, I don't know that you'll need to do it every time, but I'm literally just going to do like d dx on the left, d dx on the right. And I'm not going to actually find the derivative just yet. I'm just going to write down what I'm doing. So there's step one, right? I'm differentiating the left side, differentiating the right side with respect to x. Now, eventually, we'll get to from dy dx to dy dt or dy dh or dr dt, like the variable that we're differentiating and the one that we're doing it with respect to will kind of change as we apply this to something. And so this skill is just learning the skill these first couple of days, and then we attach it to something. Now, okay. Now we look at the left-hand side. So, okay, how do I take the derivative with respect to x of a couple things being added together? Well, just like we always have, take the derivative of each one separately. Right? The derivative of x squared, the derivative of y squared, whatever I got, I'll just kind of break it apart. And so again, I don't know that you need to write this step, but this is what I'm going to do. I'm going to do d dx of that plus d dx of this. I'm not going to do anything here just yet. I'm going to take my time. Right? I'm going to find the derivative with respect to x of x squared, the derivative with respect to x of y squared, and the derivative with respect to x of 25. Now, the reason I can break that apart and take each individual derivative is because things are just added together. Right? If that was a product inside there, I need a product rule. Okay. Then I'll do it. U and V and du and dv. And we'll see what we get. If it was a quotient, cool. If I needed the chain rule, fine. I'll do whatever I need to do in each one. But I want to kind of make it as simple as I can, as often as I can. I want it to be nice. And now that it's kind of broken up into those three little pieces, now let's individually take these derivatives. What is the derivative of x squared with respect to x? 2x, yay, life is good. And what's nice about that, I'm gonna write something right after that x here for a second, just so you can see why it works. When the variables match, right, with respect to x, and it's got an x in it, we're good. Right? I'm taking the derivative of x squared with respect to x. Okay, cool, those match, so I'm taking the derivative, and I can just use whatever rule I need. Right? I have my trig derivatives, I've got my power rule right here, which is nice. If it was a quotient, cool, I'll do that, whatever I've got. When the variable matches, I don't really need to say, here's what I'm doing. I'm taking the derivative with respect to x. But really what's happened here, and if you'll allow me to do this, you don't necessarily have to write this down, but like, we're kind of like leaning on the chain rule to say, okay, I'm going to drop the 2 in front. I'm going to leave the inside the same. I'm going to decrease the exponent by 1. And then I'm going to multiply by the derivative of the inside. Kind of like a chain rule thing happening. Okay, I'm going to do the derivative of the inside with respect to x. But what is the derivative of x? 1. And so we never really needed it, right? And even this notation kind of lends itself nicely. Like this just looks like a fraction that would cancel each other out. And that's why the notation is really helpful for us. Of course, it's not really a fraction dx over dx. It's notation that just means the derivative of something, but that is 1. But we never needed that, right? I never needed to really use the chain rule with a power because we figured out the shortcut to get us there. But that is kind of happening sneaky in the background. Now, why am I taking all this time to say that? Well, now look at what happens with the next one. These are almost the same exact terms, right? X squared, y squared, something squared. But if we take the mental pathway to this derivative, that's the slow but steady approach that says, okay, if I can apply a chain rule perspective to what I've got, I think it's going to help you see why what I'm going to say in step 2, this whole how-to thing, why we're going to do what we're going to do. So, the derivative with respect to x for x squared was just 2x. But really, it's 2x times dx dx. Right? Little chain rule application, and the derivative of x is just 1, so we're good. That would make me so happy. Let's do it. Like, y, let's do the chain rule, okay? 2 drops in front. Inside stays the same. Decrease the power by 1. But now what I need attached to that is the derivative of the inside with respect to x. The derivative of y with respect to x. Right? Because this was, okay, d dx of x squared. Okay, drop the x1 in front, leave the inside the same, decrease the power by 1, multiplied by the derivative of the inside. Right? Same thing. d dx of y squared. Okay, drop the 2 in front, leave the inside the same, decrease the power by 1, and then multiply by the derivative of the inside. The derivative of y with respect to x. What is the derivative of y with respect to x? Say, the derivative of y with respect to x. The derivative of y with respect to x. Nicely done. See your senioritis right here. I got this.
Excuse me, Roche, may I bring that Evelyn Clark come and sign out?
She's on her way.
Thank you.
Thanks. So here's basically what happens. Okay, this whole chain rule idea really kind of boils down to just this, and I want to make sure that I write it down the same way that I do in the document that I'm going to share with you. Anytime we differentiate by having a y term, so a term that has y in it. Now, maybe that's part of a product or part of a quotient or part of the chain, but whatever. Anytime you differentiate something that has y in it, okay, what we'll need to do is we will need to attach a factor of dy dx. And really, we've been doing that the whole time. When it was y equals whatever, and we took the derivative of the left side, we just wrote it dy dx. And that's what we're doing here. Whenever you've got a derivative, and you're taking it with respect to x, but it's something else, those variables don't match. When the variables don't match, we need a ddx of whatever that variable is. Or ddt or ddr or whatever variable we're looking at. But really what's happening is just a chain. Okay, drop the 2 in front, leave the inside the same, decrease the power by 1, multiplied by the derivative of the inside. The derivative of the inside is literally just dy dx. If it doesn't have a y in it, don't stress the whole dy dx part showing up. It can't be there unless there's a y. So look at the right side. Is there a y over there? No. So what's the derivative of any constant, let alone 25? The derivative of a constant. 0.
I knew that. I'll just do it for you.
Now, what happens in this case is nice. That there's only one dy dx in our implicitly differentiated equation. Okay, so if there's only one dy dx, how do you think? Because, well, here's what we're trying to do, right? Get to dy dx equals. I want to find some equation whose job is to represent the rate of change for whatever the graph that I'm looking at, right? I want the slope of the tangent line at any spot. So in this case, right, we only have one dy dx. I'm going to get rid of this because we don't need that anymore. I'm going to scoot this over so it looks a little bit more connected, right? That's kind of what we end up with, right? 2x plus 2y dy dx equals 0. If there's only one of them, and we want to get to dy dx equals, like, move stuff around, right? All you got to do is solve for it. Add, subtract, multiply, divide, whatever it is, solve for it directly. Solve for it directly is what that says. Do whatever you need to do to get that term alone. Directly, yeah. Solve for it directly. You don't have to worry about tricky algebraic maneuvers here. We'll add and subtract, we'll multiply, divide, we'll square and square root if we need to, whatever. We'll just solve for it algebraically. So what could we do to that equation on the left side in red there to start getting dy dx by itself? I heard whispers.
Divide away dy dx, like put it on the other side.
But if I divide it away on the, like, I would have to divide it everywhere. Divide it here, divide it there, and divide it there. Let's move the 2x over first before we start trying to break these two apart. So I like that. So let's subtract 2x on both sides. We always add or subtract before we multiply or divide because it's kind of works its way from the simplest part of order of operations, kind of moving on. So 2y dy dx, that's a y, equals negative 2x. Now we can divide by 2y. That sounds good. So divide by 2y on both sides. So dy dx equals negative. The 2's will cancel. So x over y. And there's the derivative of this circle. There's an equation whose job is to say, okay, give me not just an x anymore, but an x and a y. Because give me an x value, I don't know which y you want me to be at. And clearly, where I am on the circle, I'm going to be drawing very different tangent lines in certain spots. And so this equation has both x and y in it, which means we will need like both the x and the y along the circle, or whatever shape we're looking at, in order to find the slope of the tangent line at that spot, in order to find the rate of change as we move from left to right. Now, like along a circle, like you think about like going clockwise or going counterclockwise. No, we go left to right still. And so once I stop, I'm thinking about what direction I'm pointing once I get there. There it is, negative x over y. Now, the situation that's going to come up is if there's more than one. Okay, now we're going to get to that at the end here. So I'm going to leave this blank here for just a minute. So if there's more than one dy dx in the problem, we'll just have to kind of solve for it slightly different. Let's do one more kind of like this one before we get into that.
I agree.
Questions about this process, though? I know it'll be a little new to start, but it's not any new skills necessarily. You just have to say, oh, it's got a y in it, cool, dy dx. Like right at the end, always attach a little dy dx, and we're good to go based on the idea of the chief. Right? So we'll fill in the rest of number 2 there here in a second. Okay, go ahead and turn the page. Let's do the same thing, but they're going to put the circle somewhere else. Do you know where the circle used to be centered when it was just x squared plus y squared? The origin, yeah.
Oh, it's an origin.
X squared plus y squared. If there's nothing moving it left or right, up or down, it's the center of the origin. What's the radius if it was equal to 25? By the square root, right? Because every circle's general equation looks like this: x minus h squared plus y minus k squared equals r squared. Okay, where the center is hk, center is hk, and of course the radius is going to be your r. And so x squared plus y squared equals 25. Yep, centered at the origin because we didn't add or subtract anything inside, and it was equal to 25, so we'll square it. So now they give us the picture, but we don't have the equation, so it's up to us first to find that equation, and then we'll find the derivative. So take a look at the next page here where that circle is drawn. Really all we need to do is figure out the center and then kind of measure out the radius. Where do you think, so x minus plus y minus, I can do that, and then I'll just put the right numbers in. Where's the center? Looks like 3, -2. That looks pretty centered to me. So x minus 3 and then y plus 2. And then what's the radius? Measure a straight distance from the center to the circle. So equal to?
25.
So very similar equation. It's the same circle, just kind of moved over. Which means that its derivative is probably pretty similar, but the fact that the center is somewhere else, I think, is going to adjust parts of this derivative. Right? Now we have that, I'm going to blow this up so I can write a little bit more in the space. Okay, cool. All right, I'm going to make myself just a little bit more room so I can do some derivations. I'm going to slide this up, but that's the equation. X minus 3 squared plus y plus 2 squared equals 25. Okay, let's differentiate both sides with respect to x. So d dx of the left. Again, I think early on it's worth writing these kind of steps down, but once you get used to it, you'll know what to do. All right, so here's the left side. Bless you. Again, I don't break anything up right away. I just say, okay, I'm going to differentiate the left. I'm going to differentiate the right. I'm going to see what I get. Because now what I'm hoping to do is make kind of this big, crazier like equation that I've got with differentials on everything. I want to slow myself down and break it up into as many small derivatives as I can. And then I'll just attack each one separately. And just like we did for the other one when it was x squared plus y squared inside, we're like, okay, I can just find the derivative of x squared because that's one term, derivative of y squared, that's another. How many terms do we have here on the left side? Still 2, so I can do it again. I can say, all right, let me deal with this derivative first, d dx, I'm just going to stick with the blue, of x minus 3 squared. I'll find that derivative, plus, then I'll find this one, y plus 2 squared. And then I'll find this one. Again, I could do some work here, but I'm trying to go slow so that we can take our time, get it right early, and then we'll get a whole lot better over these next couple of days. Okay, so take a look in this first one. The derivative with respect to x of something that has x in it only. Sweet. I don't need a dy dx in there. I'm just going to find that derivative however I need to. Power rule, product rule, quotient rule, chain rule, trig, whatever, right? Whatever, exponentials, logs. I have all of these things from chapter 3, all of the rules for derivatives. Now I just need to apply them. What do we need here, just in that first one, in order to find the derivative of x minus 3 quantity squared? I mean, we could expand it. And then find each derivative there. Or chain rule. We just use chain rule. The thing that I like about the chain rule is I don't have to move anything around. I can just do it, right? Exponent goes in front. Leave the inside the same. Decrease the power by 1 and multiply by the derivative of the inside. 1. Yay, that's good. I like multiplying by 1. Sweet. Now, do I need the exponent of 1 or the times 1? No, eventually I'll just get rid of those. But I'm going to take my time here and show you that I'm using the chain rule. Okay, now, same thing with d dx of y plus 2 squared. And as you're working through these initial derivatives, I think another important piece of advice that I can give you is while you're doing the work, Don't stress the difference between whether x is there or y. Find the derivative as if it was just x. But keep in the back of your mind, oh, there's a y there. Eventually, I just need a dy dx. I just got to attach a factor of that at the end. So treat that second derivative as if it was exactly the same as the first. Y plus 2 squared. Just think x plus 2 squared. Think of it the same way. Just keep in mind that there's a y there. What do we need to find the derivative of x plus 2 quantity squared? Chain rule. Drop the exponent in front. Leave the inside the same. Decrease the power by 1, and then multiply by the derivative of the inside. The derivative of y plus 2 is dy dx. And there's that factor that I needed. It's going to come up naturally as you take your derivative. Now, if that was like y squared plus 2y plus 3 inside, and then it was squared, okay, then I've got some more work to do in here to find that derivative. They're going to keep it simple to start and just have like a y or a y squared or whatever. Sweet. Nice. The derivative of 25 with respect to x? Still 0. Now, okay, let me clean this up a little bit, and you can just do it like right there. I'm just going to take one extra little line of work to do. Okay, 2 times x minus 3 plus 2 times y plus 2. Again, I'm not going to distribute and make this whole big mess. I'm going to leave things factored. I want you to focus on the calculus part, not the algebra. Okay, how many dy dx's do we have in the problem? 1. Then let's go get it. Just go solve for it. And solve for it exactly the same way we just did. Before it was 2x plus 2y dy dx. We subtracted 2x and then divided by 2y. Same thing. It's just not 2x anymore. Now it's 2x minus 3. And last time we subtracted 2x on both sides. What should we subtract on both sides now? The whole thing. Slide it over. Right? It's connected. We can just subtract it over. 2y plus 2 dy dx equals negative 2x minus 3. It's the same idea, which is nice, which is why I like to do those two problems back to back. Right, got to there, we looked good. Dy dx is starting to get isolated. That's what I'm trying to do. Last problem, we divided by 2y. Now what should we divide by? 2y plus 2. And here's what's nice about keeping things factored and not multiplying things in. If I divide on both sides by this, what's going to cancel? Those 2's are gone, just like they did last time. And so we've got negative x minus 3 over y plus 2. And that is the slope of the tangent line at any point on this graph. Again, we needed both x and y in this derivative specifically because the graph that we're looking at is not going to pass the vertical line test or the horizontal line test. For every x, almost every x, there's more than one y. And for almost every y, there's more than one x. Right? This is like the opposite of being one-to-one. And what we can do now that we have that derivative is we can actually apply it to the points in the table right below. Right? Those points that were given say, okay, let's see if we can find the slope of the tangent line. Let's see if we can find the rate of change at a couple of points along the way. Okay? Let's stop at 0, 2 and see what the value of dy dx is at each of those spots. Okay, and here's what the notation looks like. Okay? Dy dx, and then check this out. Big, long, vertical line. Goes all the way to the top, all the way to the bottom. And there's two different notations that I think are okay. You can say at 0, 2. Or, and I'll just kind of set up the one right below it, you just don't even need the at sign. Okay, either way. What you're kind of saying is, okay, like dy dx equals is like, here's an equation for every point. Doesn't matter where you are. Okay, when we actually want to evaluate it, but we can't say f prime of and like put an x in there. We need a notation that will help us say, okay, I'm going to evaluate the function at a specific x, a specific y, or in this case, at a specific point xy. And what we've got is an equation that can do that for us. Negative something, right? X and y have their spots. What was it? Minus 3 plus 2? So let me stick with the color. So minus 3 plus 2. So the only evaluating that happens is the x and the y just go away. All right, so dy dx at 0, 2. Said, oh, well, all right, take that dy dx equation that you found and just plug in an x, plug in a y. Let's see what we get. So negative, let's see, negative 3 over 4. So 3/4. So depending on how it all works out, maybe you need just the x to plug it in, cool. Maybe you need just a y to plug it in, great. Maybe you need both. Now let's see if that actually makes sense. Can we go to this graph right here and say, okay, at 0, 2, there's a point right there. Can I draw a good estimate for the tangent line at that spot? And if I can, does it have that slope? Well, for me, I already know the slope. Let me draw a line with that slope that goes through this point and see if it looks good. So 3/4, so 1, 2, 3. So up 3, 1, 2, 3, over 4. And then I'm going to go in the other direction. Down 1, 2, 3, 1, 2, 3, 4. And sometimes you don't have room to actually get yourself 3 lattice points, and you just have to do the best you can. This is big enough where I can. If I connect all those 3 points with a straight line, now maybe you're freehanding, I'm definitely freehanding. Maybe you just take out the edge of a notebook or whatever, try to estimate as best you can a straight line. Ooh, that was a good one. That looks pretty darn good to me. And that's what's so nice about implicit. And really, we've been doing implicit differentiation this whole time. All of the dx's have just been 1. We just never needed them, which is good. I don't want to write things I don't need. But now that we've got these equations that just aren't functions explicitly defined in terms of x, implicit differentiation can kind of take control and allow us to handle it by just doing ddx at both sides, or ddt or dd or whatever we'll do by the end of next week, beginning of the week after. So seniors, you'll probably just get mostly implicit practice and maybe a day of actually applying them on Thursday. We'll see how tomorrow goes. And we'll see if I'm here on Wednesday. Kind of depends on my schedule. Beautiful. Let's do another one. I like it. Let's do 3, see what we get, and see if the result that we get actually kind of matches what should happen on the graph. So negative some stuff. Okay, I'm going to change the color for what's going in. The 3 up there, the 3 down there. Should be 3 minus 3 on top, and then 3 plus 2 on the bottom. So negative, let's see, 0 over 5? What's that? 0. What type of line has a slope of 0? Horizontal. And if I have a horizontal tangent line, what kind of visual do I expect to see on the graph if the slope of my line is 0? Straight line, straight across, that horizontal tangent line good. What could be happening at that point if my derivative is 0? Could be a relative max or relative min. It's definitely a critical value. That's the word you're thinking of. Could be a critical value. Now, go to the point 3, 3. Is that at the top of this circle? Perfect. So it makes sense. So go ahead, draw a little horizontal line at the top there for 3, 3. This, of course, is a horizontal tangent. Now, maybe it's a max. Maybe it's a min. Maybe not. Right? Could be an inflection point, like Delaney was saying. Definitely could be. Right? Could be a max, a min, or it's just an inflection point. The second half of this chapter gets into the discussion of, like, how do I know for sure it's an inflection point? And that has to do with the second derivative. the sign of the second derivative will tell us what kind of critical value it's at. All right, let's do one more. Let's do 8 negative 2, and I think that's enough. So dy dx evaluated at 8 negative 2. I'm not going to put the at. I think it's clear. What I'm going to do, especially that my work after kind of follows, so that's cool. So 8 goes up there, negative 2 down here. So that's the only thing that changes, is I just kind of drop the numbers in wherever there's an x and a y. And like I said, you don't have to have both x and y. Sometimes you do. Okay, so negative 5 over 0. So we're at a point on the circle, 8, negative 2. Point's defined for sure, right? X squared plus y squared, basically. Right? Plug in any point I want. I'm not, my range and my domain aren't infinite. I'm just trying to find values that equal 25 once I do it. Some nice ones, some not nice ones. But either way, we find this derivative, and what is negative 5 over 0? How should we write that? Undefined. And so the point on the graph exists, but the derivative does not. Now, go to 8, negative 2. Draw a line tangent at that spot. What do you think that looks like? All the way on the right side there, what type of line, what shape, like what slope is undefined? A vertical tangent line. Okay? And so that's one possibility. Okay? When you've got a slope that's undefined, right? You've got a rise, the 5, right? But no run. Right? When you think about, remember, dy dx is just slope of the tangent line, rise over run. And we have them written as fractions, which makes it even nicer. I'm going up or down 5 to get from one point to the next, but going left to right, 0. That's going to give me a vertical tangent line. That is one way that a function can be defined, or a relation, I should say. A relation can be defined, but the derivative at that spot is not. A vertical tangent line is one. And I showed it to you last time, but a cusp, a sharp turn would be the other. And we'll see that a little bit again. Okay, we have 5 minutes, so I wanted to do one where there's more than one dy dx, just so you can see it. So then tomorrow, Wednesday, we can kind of get after. So I'm going to leave the rest of those blank. We're just going to do this one, the top left, next page. This will be our first and only derivative that we do implicit today that has 2 different values of y in it, right? And when you see those 2 different powers of y, that's kind of a clue to me that, number one, explicit is never going to happen. I'm never going to get this to be y equals, so I might as well just get after it and go implicit by taking the derivative with respect to x, right? And how do I know that that's the variable I should use? Look what they asked. Find dy dx. If that said find dx dy, or find dy dt, something like that, that would be my clue that I would have to do something different. I would have to differentiate with respect to something else. But they want dy dx, so I'm going to take ddx on the left, and I will take ddx on the right. Okay, and eventually over here, I'm going to continue the how-to from the page before, which you can just like flip back and forth to do it. We'll get to 2, and we will finally answer the question if we have more than one dy dx, what do we do? All right, so let's do it. The derivative of the left-hand side, so I'm going to rewrite it again. Maybe you don't have to at this point, but because I've got those 2 different terms on the right, I can take their derivatives separately. And the step in blue, I think, is one that's helpful to write down early, but eventually that becomes a mental step that you take to get from one line in red down to this next one. And the only thing that I think you really have to remember is that, number one, so maybe 2 things, it's twofold. Number one, treat every derivative as if it was x. Okay, but if it's not x, then attach a dy dx. It's a little chain rule action. So the derivative of the left side. If that was just x squared, then it would be 2x. But now it's y squared. So 2y, and then, oh, it's a y? Okay, dy dx. Treat it just like x. Do whatever you need to. Power rule, product rule, quotient rule, chain rule, whatever. Do what you got to do. And then, oh, it's a y? Okay, cool. Little factor dy dx. Okay, derivative of 2x. To the slope, right? It's linear, so drop the 2 in front, decrease the power by 1, 2x to the 0, if that helps. Okay, and then what's the derivative of 3y? Well, think of it like 3x, and then attach a dy dx. 3 dy dx. And there it is. There's our second dy dx. And so our job is to get one single dy dx alone on the left, and everything else on the right. And so the problem that we have is we've got two different ones. If there was just one, we would just solve for it directly by moving everything around. But now you've got this over here. And so I think the mindset, don't write this down, but I just wanted to give you something to look at so you can envision it. Imagine trying to solve this equation. 2x equals 2 plus 3x. 2y dy dx plus 2 plus 3 dy dx. Similar. Not exactly the same, but similar. Right? X is on both sides. How do you solve an equation like that one in blue on the right? Yeah. Subtract 3x, right? Because I can get my x's onto the same side, and if they have the exact same thing, like kind of take away the constants, then we can just combine them together. Right, subtracting the 3x from the left and the right, eventually I would get to here. And then I would, great, now they're together and I can just solve for it directly. Right, subtracting 3x on both sides. But the problem with this is that if I subtract 3, not x, but 3 dy dx on both sides, well, hey, at least these cancel, that's good. So I'm just going to be left with 2 on the right side. This one's got a y and this one doesn't. It's kind of like me doing this. Right? If I attach a y to that one right there, and I subtract 3x on both sides, minus 3x, minus 3x, can I put those together? No. And so same thing is going to be true here. There's really nothing I can do to put them together, so I just write them side by side. 2y dy dx minus 3 dy dx equals 2. So if you've got more than one dy dx, I think a really good strategy is to move, gosh, I wish this would read my fingers, but move all dy dx to the left. So if you want to go back a couple pages, move all of your dy dx's to the left-hand side, get them onto the same side, and if necessary, move everything else to the right. Okay? And everything else to the left. Let's just finish this one and then I'll let you guys go. Because we're not there yet. We don't have dy dx yet. To the right, to the right, to the right. Move all your dy dx's to the left. Move everything else to the right. Sorry about that. Okay, now what? How are we going to rewrite this equation in red so that there is only a single dy dx to solve? Brady. Every single time. Factor out dy dx. Because it's in common with everything over here, because we moved everything that had one to the left and everything that didn't went to the right. In this case, we didn't have to move anything from the left to the right, but sometimes it will. And then one last step. Once you factor it out, how are you going to get it by itself? Divide. Dy dx equals 2 over 2y minus 3. Voila. There you did it. Okay, and what's nice is that plan always works. You get more than one, move all of them to the left, everything else to the right, factor, and divide. Okay, have a good day. I will see you tomorrow. Nothing you need to do for me until then. We'll have some time to recap, practice, work on some stuff, and I'll hopefully have some grades for you.
Thank you.
Thanks, everybody.
Thank you,
Bye.
Yeah.
So for the Unit 4 test, I'm trying to figure out like a schedule for travel and wrestling.
Cool.
I was wondering if I'd be able to take that like that Wednesday before or after school.
Which Wednesday?
Like so we don't have school that Thursday, so it's like.
Right, the
It's the first
19th.
day of finals.
So you want to take, so do you have a first or a second?
Yeah, I have the first and the second.
I still have yours from last year.
I would probably.
You can do that afternoon.
I could probably do it or
Or like right after.
like that Monday, so I don't have the 5th or the 6th.
The Monday after?
Yeah.
That's fine.
All right.
Yeah, either one works.
All right.
Yeah.
I'll email you when
Just
I
let me
know.
know.
All right.
I have two.
That's like great.
I have
The Rock.
on Wednesday and Thursday.
This week.
Yes.
What do you got?
I know.
AP, US history, and
Okay.
Okay.
So I think probably missing class.
Okay.
I just wanted to let you know.
So the plan for me with all this stuff is to give us a lot of implicit practice first.
Okay.
And so that's probably all we'll do. We might get to the point by Thursday where we actually apply this. Let me show you kind of what's coming down the road here. So practice, 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 practice.
Okay.
Apply it. When does it have a horizontal tangent? Oh, we'll find the derivative, set equal to 0. When will it have a vertical tangent? Just find the derivative, figure out what's going to make it undefined.
Okay.
Practice, practice. Practice, 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 practice. Lots of practice. Ooh, an AP question or two. So we can practice kind of what it looks like just to see it from the AP side. But then what we do from there is now we take actual meaningful equations, not just some random x's and y's and whatever all over the place. We will actually figure out how the surface area of a sphere can change as the radius gets bigger or smaller. How is the volume of the sphere going to change as the radius gets bigger or smaller? Right? How is the volume of a cylinder going to change as the radius gets bigger or smaller and the height gets bigger or smaller? So we have what's called, and this is what you'll think about kind of coming up, is related rates. I can figure out how one rate is changing if I have another. Like imagine blowing up a balloon, right? Putting air in, so the volume is changing. Well, how does the radius change with that? And that's kind of the plan. So, of course, AP test way more important than the last couple of things here at the end.
No, this is.
So, but it does get fun and interesting, and actually, like, we can apply it to because we've just been doing calculus just to learn it. Now we can actually do calculus to like, and what's nice is like they lay out a really nice, easy plan for us.
Cool.
Stone is dropped into a calm body of water, causing ripples. Like
Wow.
we can look at kind of interesting things. Water's leaking out of a tank that's a cylinder. A cone, like we pour water into a cone at a certain rate, and like all of this stuff, which is really fun. A ladder is leaning along the side of a house. Like you can imagine pictures that look like, you can see how far I have to go to get like, but it's just practice, 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 practice. There we go.
Oh,
Right?
yeah.
Like when pouring water into the top or like cutting a hole in the bottom and watching it drip out. Right? Like two ships are like moving in different directions and there's a lighthouse that we want to make sure that they don't run into the lighthouse, but they don't run into each other. Like how does all that stuff work? A ladder leaning up against the side of a building. Like what if I kicked like the bottom of the ladder out? So that side moves, so obviously the top has to move too.
Yeah.
And so all that kind of stuff. So kind of fun.
Cool.
But yeah, sounds good. Thanks for the heads up.
Yes.
We'll just practice.
I just wanted to let you know.
Awesome.
Also, I was wondering if I could know what I got on my 3.2 quiz.
Sure.
That one was scary, Mr. Rose.
Was it?
Yeah. I
The
thought
front
I-
was easy, the back was hard, right?
Yeah.
Brady.
I'm
45 out of
scared.
50.
Oh.
Yeah.
that's
And you
better
wrote
than
at the
I
top,
thought.
like, I'm so sorry, I got
Yeah,
lost.
I
And
really
you're going to
thought
see
I
me
was
write it.
doing
I was like,
really
no, you
bad.
did great.
I thought
It
it'd
was
be a lot
really,
worse
here, let
than
me
that.
show it to you. It was like one silly thing on the front, and then just a couple missteps on the back.
It was my online week, so I really thought that I was gonna.
Okay.
I cannot focus at home.
No, me neither. So there are the solutions. Clearly the back has a lot more work.
Yeah.
There's yours. So yes, definitely. And the reason we can is because the base is E, so the 2 is just a constant. The coefficient. So 5 times 2, 10 coefficient. If the base was the 2, like if it was 2 to the 5x, then you can't multiply those together. Here's the silly mistake.
Oh.
right? Just
Yeah.
wrapping that in parentheses, because really ln of 10 times x squared and ln of 10 times. And then you would want to like factor the e to the negative 2x out.
Oh.
And then you just have one of them.
Okay.
Because really what's happening is it's like, this is over e to the 2x, and this is over e to the 2x.
I wonder why I did.
Here's what I was talking about. The 2 is the base, the 4 is the coefficient. You cannot multiply. So
Okay.
we just leave it 4 times. And then you went from adding to multiplying. So
But.
instead of just saying, oh, 2x minus 2x is gone, negative 1 minus 6, negative 7. So your numerator just.
Cool.
Yeah. So just a couple of things, but I don't know. Pretty good.
All right, good. Thanks, Mr.
You're welcome.
Rembrandt. Thank you. Have a nice day.
Yeah, I'll see you tomorrow though, right?
Yes, I will
Okay,
be
good.
here tomorrow.
Sweet.
Thank you.
Bye.